Hello everybody, sorry I'm not there today. I am homesick, excuse me, but we're going to keep moving on. In your folders last time you had 3 green sheets. We filled out the first one on graphing. Today we're going to, in this video, talk about the second one that says solving systems of linear equations using substitution. And again, we're using substitution. So I want you to think about for a second what the word substitution means. Okay? When you have a substitute teacher like you do today, they are taking the place of me, acting as me. So we're going to think of it in the same way in math, that I can substitute something else in for another thing if they are equivalent. So what do I mean by that? Let's look at example number 1. Okay. The first equation that's given is y equals 2x plus 5, and the second one that's given is 3x plus y equals 10. Now, if you remember last class, we talked about the fact that when we have two unknowns in these cases, the x's and y's represent the same thing, meaning the x in both equations represents the same number, and the y in both equations represents the same number. So when we were looking at solving these graphically, we were looking for where do the two lines cross. We said there's 3 possibilities. You could have in a graph where they cross once, something like this. We said another possibility was that they don't cross at all, parallel lines. Or our third option was they were the same line, so we just got the same line drawn over top of the other. These are our 3 options. More often than not, the first one is the one that we deal with. So, but you would have found in the homework that you just did that sometimes finding that graphically, just graphing the 2 lines and locating exactly where they cross can be a little bit hard. You know, if they're fractions or if we don't graph them 100% accurately, it's hard to tell where they cross. So we need some other methods to do that algebraically. The first one that we're going to talk about is substitution. Now we use substitution just the way it's termed. In our first equation here, it tells me that y is equal to 2x plus 5. That means these two things are equivalent to each other. So because the y variable in the second equation represents the same y in the first equation, I can replace anywhere I see a y in the second equation with 2x plus 5. So I'm going to go ahead and do that. I'm going to plug in 2x plus 5 where I see y in the second equation. So that leaves me with 3x plus, and then I plug in the 2x plus 5 in place of the y in the other. Now why I want to do that is because notice my equation now is all in terms of x. Excuse me. So I'm going to combine my like terms. I've got 3x's plus 2x's gives me 5x's plus 5 is equal to 10. What this allows me to do now is to solve this equation for x and then use that x value back up in one of these 2 equations to determine the y value. So, okay, I'm going to get x by itself then. So first step is going to be to subtract the 5. So that leaves me with 5x equals 5. And then get rid of the 5 times x so that I get x equals 1. Okay, so now that I know that x equals 1 is where these 2 lines cross, since they share the common x value of 1 and we're looking for where these 2 lines cross, then I can plug in that x equals 1 into either of these equations to get the y value because the 2 lines share that same point. So you can plug it into either one, and I'll show you that it works for both. So we could plug it into y equals 2 times 1 plus 5, which gives us 7. If I used the other equation, I get 3 times 1 plus y equals 10. So I have 3 plus y equals 10. Subtract the 3 from both sides, and I still get y equals 7. So notice they're the same thing. So my solution, which is our point of intersection, is, and we're going to write it as a point, the x value of 1, the y value of 7. So had I graphed these two lines, I would have been able to see that they crossed at the point 1, 7. Let's look at example number 2. Now you'll notice it gives us the two equations, 3x plus 4y equals 8, and x equals 16 minus 4y. So in this case, I notice that in the second equation it tells me x is equivalent to 16 minus 4y. So I'm going to take this 16 minus 4y and put it in for x in the equation above, because it's telling me that x is the same thing. They're equivalent. That's what equals mean. So I'm going to go down here and I have 3 plugging in the 16 minus 4y for y, or for x, excuse me. Leave the rest of it the same. Now you'll notice your equation is all in terms of y. Okay, so I need to first, before I can do anything, I need to carry through this 3. 3 times 16 is 48. 3 times negative 4y is minus 12y. And then the rest of it stays the same. Okay, so that gives me 48. I'm going to combine the negative 12 and the plus 4. So that gives me negative 8y. And I want to get y by itself. So I'm going to subtract the 48 from both sides. And I'm left with negative 8 equals negative 40. Oh, negative 8y, excuse me. And then divide both sides by negative 8. So I am left with y equals 5. Now, since this is the point on the y-axis that both of these lines share, you can plug it back into either of these. I'm going to use the x equals because it's already solved for x. So I've got x equals, and it's 16 minus 4y. So I've got 16 minus 4 times my newly found y value. So I've got x equals 16 minus 20, which is negative 4. So my solution, the point of intersection, is x value. X always goes first. Even though we found 5 first, that's the y value. So if I were to have graphed these two lines, I would have gotten that they cross at the point negative 4, 5. What happens, though, when neither equation is solved so that it says x or y or some variable equals? So in example number 3, it does just that. It says x plus 4y equals 9, and x minus y equals 4. So now you have to choose. Okay, you look at one of your equations. If I'm going to use substitution, I need one of them to say either x equals or y equals. It doesn't matter which variable you choose to solve for. You might want to make it so it's y equals. I'm going to do this equation twice, or this particular example twice. Once we're going to solve one of the equations for x, and once we'll solve it for y, just so you can see both methods. Let's start with solving for x. I notice I'm going to take this first equation and I'm going to solve it so it says x equals. So I'm just going to rewrite it down here. In order to get x equals, I need to get rid of the 4y. So I'm going to subtract the 4y from both sides. So that leaves me with x equals 9 minus 4y. So I'm going to take this 9 minus 4y and I'm going to plug it in where it says x in the other equation. So now I've got 9 minus 4y in place of x minus y equals 4. So negative 4y and negative y combined together give me negative 5y. And then I'm going to subtract my 9 from both sides so that I have negative 5y equals negative 5. And divide both sides by 5, negative 5, and I get y equals 1. Alright, so now if I want the x value, I can plug it into either of the original equations and it works. Or I could plug it into the one that I rearranged. Doesn't matter which one you choose, it's all means the same. So now I've got x plus 4 times 1 equals 9. X plus 4 equals 9. So I'm going to subtract the 4 from both sides, and I get x equals 5. So my solution, the point of intersection, is at x comma y, 5 comma 1. Now I'm going to redo this again and solve the first equation for y, just so you can see how it works. So let's do this. I'm going to do this one again. So I'm going to choose to do x plus 4y equals 9 and x minus y equals 4. So I'm going to solve so that it says y equals. So I've got x plus 4y. I'm just going to rewrite it. And I'm going to get rid of the x instead. So I've got 4y equals 9 minus x. And divide everything by 4. Makes it look a little yucky, but that's okay. So I've got y equals 9 over 4 minus 1/4 x. So I can take this and plug it back into the other equation where it says y. So now I have x minus the quantity of 9 over 4 minus 1 over 4x, and that needs to equal, I ran out of space, but it needs to equal 4. So it's a little yucky, but we can deal with it. So we've got x minus 9/4. I've got to carry this negative through. And negative times a negative is a positive. So I've got this weird x minus 9/4 plus 1/4. So if I treat, that's a 1. If I make it a 4 over 4, if I add, I've got a 5 over 4x minus 9 over 4. And since we're dealing with 4s over 4s, I'm going to make this 16 over 4. Okay, so now I need to get the 5 over 4x by itself, so I'm going to add the 9/4 to both sides. So 16 plus 9 is 25. That should be an equals. So now, think back to when we were doing this. If I have a fraction times x, if I want to get rid of the times, we would think divide. But when we're dealing with fractions, that's the same thing as multiplying by the reciprocal. So I get 25 times 4 is 100. 4 times 5 is 20. And 100 divided by 20 is 5. So I get x equals 5, and then I can plug that back in. 9/4 minus 1 over 4 times, and I'm going to make that a 5 over 1. So that's 9 over 4 minus 5 over 4, which is 4 over 4, or 1. So a little uglier way of doing it, but we got there. So my solution was x of 5 comma y, which is 1. So I'm going to have posted up here a worksheet for you to give some of these a try and during class, and then your homework is posted on the portal. We will do the elimination method, the third green sheet, next class. And if you have any questions, please feel free to email me, and I will we'll see you in class next time.